is about why so much of emphasis in this course on metric spaces. I hope the person who asked this question will be definitely there. Anyway, this will be of interest to everybody. So this itself can be a full lecture, but I will give it short. The point is, topology arose out of the study of metric spaces as a first generalization to the study of functions on R and R2 and R3 and so on. The first generalization. If you look at the epsilon delta definition of continuity, it is there built in only on metric spaces. More general topological spaces cannot give epsilon delta definition. Okay. Even the concept of limit, concept of open set, all these things arose while studying the real line and its behavior, and later on R2 and its behavior, R3 and its behavior. Real valued functions defined on some open subsets of Rn. Indeed, as far as analysis is concerned, you actually study more than just a metric space, namely the norm linear spaces, the Banach spaces, the Hilbert spaces, and such things. So Banach spaces take the cake, and when you study topological aspects of analysis. So you can see that even in part 2, I have brought back the Banach spaces again. Okay. So that must be a reasonably sufficient answer to this question. If you want more elaboration, you can still ask me. All right? The second question is also quite relevant. The second question is, what is the extra property of Rm as compared to Rn when m is bigger than n? I will slightly change the question, which is also part of the question whichever has been answered. Why Rm and Rn are not homeomorphic when n is not equal to m? The answer is quite interesting. It will take you quite deeper into topology, but it is not easy. Classically, this question was one of the motives to introduce the so-called homology theory by Prof. Of course, his methods and later on efforts have found proofs within the topology itself, and I have taken quite some time to introduce that kind of approach in part 2 of this course. In part 1 you will not see. Nevertheless, for example, if you want to just see S1, R1, namely real line, why it is not homeomorphic to the R2, for example, you can give an easier proof. Okay. Easy proofs are possible whenever you specialize to some simpler situations. Suppose you want to ask why R1 is not homeomorphic to R3, R4 and so on. That is possible. Okay, you can try it as an exercise. When I say possible, possible within the very discourse itself, point-set-topology, part 1, whatever you learn here, that's enough to answer this one. But suppose I want to show general question Rm not homeomorphic to Rm, that will be very difficult. Okay. If you take linear isomorphism, then you know the answer is from vector spaces. Okay, that is the starting point anyway. If n is different from m, an m-dimensional vector space will not be isomorphic to n-dimensional vector space. Dimension of a vector space is an inherent property of isomorphism property. Okay, that is easy to see from linear algebra. But if you don't bring the algebra there, just ask for 1 continuous and the inverse also continuous, I mean just homeomorphism, then linear algebra will not help. Nevertheless, within topology there is a concept of what is a dimension. In part 2, I deal with one chapter completely on dimensions and establish that open subsets of Rn have exactly dimension n. So if you take an open subset of the real line and open subset of R2, okay, then their dimensions will be different. Now it is not very difficult, of course I haven't defined what is the topological dimension, but if you go through the definition of dimension, it is difficult, it's not difficult to see that it's a topological invariant. Therefore, open subsets, non-empty open subsets of R1 and R2, Rn and Rm cannot be homeomorphic. That will be the final answer. Okay. But that means we have to study what is the meaning of topological dimension and develop that theory. So that is done in part 2. I emphasize, if you just want to see why an open interval in R is not homeomorphic to an open disk inside R2, then it is easy to see. I will not tell you the answer, you try it out. Now it is time for me to give you some time to write down your queries, any more queries if you have. Okay? Okay, there is one correct answer here. Connectedness will work for the question that I have asked. Congratulations. Akash Pradhan has a right answer. The details, I hope he knows how to write down. Once he has given the correct answer, use the connectedness. Connectedness of what, etc. you have to write down. Work out properly. If no queries come, maybe for the benefit of those who are attending, I can tell you something. Indeed, I am not supposed to do anything more than what has been already done in the regular lectures. Nevertheless, whatever I say today, you can be sure that they will not be asked in the exam. With that topology, let me tell you something. You have, so far, you have studied three important theorems on metric spaces, right? So one of them is the Banach Bayes category theorem. I have also told that how it is very important especially in analysis. Of course, in topology also it is important. But Bayes category theorem as such is done only in metric spaces. Later on, we will do it on complete locally compact metric spaces, etc. Similar results. So it will appear again. Right now, the application that I have given is to know that there is no function, real valued function from R to R, which has its discontinuity set, that is set of points wherein it is discontinuous, is precisely the set of irrational numbers. That means a function which is continuous at all the rationals and discontinuous all the irrationals. There is no such function. If you interchange the role, then you know already the example of Thomas, which has set off at all the rational points, all the rational points is discontinuous and irrational points is continuous. So in some sense, The set of discontinuities for these nice spaces is somewhat nice, not very wide. Namely, what we have proved is it's F sigma set. Set of discontinuities is F sigma set. Right? That's what we have proved. One can ask, take any metric space which is F sigma set and an F sigma set inside it. Take any metric space and an F sigma set inside that. Will there be a function on the space such that its set of discontinuities is precisely this subset F sigma set? Namely, the converse of whatever we have. Let me show you that screen so that it will be more accessible to you. Yeah. So this was the theorem that there is no function from R to R which is continuous or rational numbers and discontinuous or irrational numbers. Can you see the screen? So this was some theorem that we have done. We have already gone through this one. And then there is an example, this one, which is called Thome's example perhaps. Many other names are there, popcorn function, modified Dirichlet function and so on. Okay, take it to be 0 on all irrationals and 1 by q for x equal to p by q with GCD of p and q equal to 1. So these for rational numbers. Right? So now I am asking you a converse to the proposition that we had here, namely, this is the application, this is the proposition. From R to R, any function, and df is a set of all points which are where f is discontinuous, then df is an F sigma set. So this is from R to R we have done. In fact, this will be true for, instead of the domain being R, you can take any metric space which is complete. Okay? Then this is true. Because a complete metric space cannot be a bare set, that's all. So now I am asking you the converse. Okay? So come to the converse here. One may ask whether the converse of this proposition holds. Namely, take an F sigma subset F of R. Does there exist a function F from R to R such that df equal to F? This is the set of discontinuities of F. Answer is yes, and we have a need the following more general result, namely, in any topological space, which should satisfy one condition, namely such that both A and A complement, namely x minus A. Both of them must be dense. So that is the case in the case of R, you see. Rationals as well as irrationals, they are complement to each other. Union is the whole space, right? But both of them are dense. Right? So if that is the property of any topological space, then the converse will be true. Namely, given a subset F of X, the set of discontinuities a function from X to R will be precisely equal to F. It is if and only if I have stated here. Okay. Only if part is the theorem, if part is the converse now, that we have to prove. If you state it as a theorem, you have to prove it. Okay, the only if part is exactly the proposition which does not even need an extra hypothesis because it's R already. Okay, so that we have made in this theorem. Actually, you don't need any hypothesis. Namely, you just write the set and show that it is union of some countable union. So that doesn't need it. So that was a theorem actually. So for the converse, you need this extra hypothesis. Okay. Now you can offer the ask without this extra which is true. Easy examples can be given wherein this is not true. But can you really force this? That is a different question. There may be other kinds of properties which may also ensure there. So that is still an open question. So let me just give you a quick proof of this one. Okay, listen to it, learn it. Okay, this is not exactly a topology. You have to know more about the properties of the codomain now, namely R. Function is from X to R. X has some special property and that is over. But now the real line has, real numbers have interesting properties that will come out. Okay. So let us go to this proof. F sigma means what? It is countable union of closed subsets. Once something is a countable union of closed subsets, you can write it as a countable union of increasing closed subsets. So first you write it as a A1 union A2 union A3. Then you write B1 equal to A1, B2 equal to A1 union A2, B3 equal to A1 union A2 union A3, Bn equal to A1 A2 up to An union. So like that you can rewrite it as countable union but increasing also. Countability implies finiteness also, includes, okay? A finite union is also countable union. Empty also countable. So all that is done. Those cases are easier cases, they are included. You don't have to separately study them. Okay, write F as a countable union in this fashion. I have written them essence. One contained in the other. Just for the sake of definiteness, you start with the empty set. No problem. S not equal to empty set. Okay. This will include finite case also I told you. That means that the set itself is closed after. Finite union of closed sets is closed. So for closed subsets also, this will give you an answer. Okay, there is no, I don't have to study that separately. Alright, so I am going to directly define the function now. Take fx to be 0 if x is in the complement of f. You take it to be 1 by n, where this n is precisely that such that the point x is in Sn but not in Sn minus 1, and it is inside A. What is A? A is a set such that A and A complement of A are both dense in the given space X. Okay, so that is the starting assumption. So this is the assumption. A is both A and both A3 are dense subsets. Okay. Given any point of f, it will be in one of the Sns. After that, it will be there in all the Sn plus 1 and so on, because Sn is contained in Sn plus 1 and so on. You look at the first n for which x is inside Sn, the first one. If it's a point of A, you take it as just 1 by n. If it is a point of a complement, then you just write it as 1 by, not 2n, 1 by 2n pi. Make it sum 1 by 2 instead of 2n, you write it as root 2 times n. Okay, any irrational number you introduce here. Take any irrational number, divide by n. Okay, so there is some small typo here. All right. So I have taken pi, we'll see that later on. So that is for all the points inside the complement of A. Complement of A, okay. But inside Sn, not in Sn minus 1. All right. If it's not, none of in Sn, then it's 0 here. There is no problem. If it is in the complement of F altogether, then it is 0. Once inside F, it must be inside some A, some Sn. But it may be inside A or inside complement of A. So depending upon that, there are 3 cases here. Okay. Now image of X under this function contains only these values, 0 and all the 1 by n's, and also r by n's. So there is a slight error here, because this is not just 2 by n, it could be some irrational number by n also. We claim that the discontinuity set of F is precisely F. Okay. So let us start with, suppose F is in the complement of, X is in the complement of F. Suppose X is in the complement of F. Okay. Then I want to show that function is continuous at that point. So take any epsilon positive, choose n such that this 1 by n is less than epsilon. Since Sn is closed and X is not in Fn, for X is inside the complement of F, anything which is outside a closed set, the complement is open, so there will be an open substitute such that around X, such that this U is disjoint from Sn. If it disjoint from Sn, it is disjoint from all the Sn plus 1, Sn plus 2 and so on. Okay, only the first S1 to Sn minus 1 it may intersect. Okay, hence disjoint from all Sk for k less than n, it won't intersect. Okay, it may intersect Sn plus 1, Sn plus 2 and so on. Okay, some Sn it is not intersecting, because that's why I have chosen. Therefore, F of u will be a bounded subset 0 to some 1 by n. Okay, so I have put it a root 2 here, it will be smaller than that. So it's 1 by up to 1 by n. All these are bounded subset, and finitely many of them values will be there. And hence, the oscillation of F on U will be less than epsilon. Difference oscillation, remember, is nothing but modulus of Fx minus F5, where X and Y both run over the open subset. Okay. So that is less than epsilon, and that is precisely the continuity of F on U. Once it is an open subset on which it is continuous, it will continue at that point. This shows F is continuous at. Okay. So the discontinuities are inside F. Outside F, they are discontinuous. Now I have to show that all the points of F, it is discontinuous. Start with a point inside F. Once it is inside F, it is inside one of the Sns. You take the first one, so that n is unique, such that X is in Sn, but not in Sn minus 1. So that is the advantage of writing the closed subsets in the increasing form. Now again, take any open subset U around X, doesn't matter what. Then you at least one more point Y other than X, one coming from A, another coming from the complement of A. So this is the crucial property that you have to observe. Any open subset which is non-empty will intersect both A and A complement. So that is the density of A as well as A complement. Right? So now you see the trick. So that is the whole idea. If it may happen that this point y different from x inside u is in sk minus 1 for some k, okay, for some k, or y is not at all in any of the sk's and it is in the complement also. If it is in the complement, fy will be 0. If it is in sk minus 1, you can always choose k smallest like this one, sk minus 1, y is in this one. Then depending upon whether y is in A or A complement, okay, we can determine the value of fy. So here are the cases I have written down very explicitly. If x happens to be A and y is different, so y may be inside A complement, then fx will be 1 by n and fy will be 1 by k times pi. So this pi I have introduced sometimes pi. I say any rational number bigger than 1 will do. So I would like to write this as root 2 also. Okay. So that is different from all the 1 by n. That is what I want. Okay. That is one case. The second case is x is in AC and y is inside A. Then fx is 1 by n pi because x is in AC, but fy could be 1 by k or 0. Okay. Then also the difference is quite bounded kind of thing away from 0. Okay. In either case, we see that the oscillation of f on u is greater than or equal to minimum of these 4 numbers, which is a positive number. So what I have seen, for every open subset, the oscillation is bounded by the minimum of these numbers. Okay, bounded away from 0 by minimum of these numbers, which is a positive number. Okay, so write beta n to be the minimum of all these alpha kn is a minimum here. So I have denoted the minimum to be alpha kn. Depends upon n as well as k. Okay, now you look at all possible alpha n is fixed, all possible k which may occur, carrying from 1 to infinity. Okay, take the beta n to be the minimum of all these. Okay, that is also a positive number which depends only on n, because this entire set is bounded. If you take away 0, it will be bounded away from 0. If you keep k increasing, this 1 by n pi, sorry, this k pi, this will become smaller and smaller. So this will be approaching 1 by n. Okay, not 0. So this will be a bounded number away from 0. Okay. So that's what I told you. So the proof involves some interesting properties of real numbers, that's all. So it is bigger than or equal to beta n, okay, which is the minimum of all these. Okay, therefore, what I have shown, the point x oscillation is positive. So x is in df, discontinuity. Okay. One of the ways to learn is ask questions. Ask questions to yourself think about them. Go back to the whatever content you have read in the lecture notes or wherever, book or whatever. Go back. Whether your question is answered there. Implicitly, explicitly answered, everybody knows. If not, then seek advice of the teacher or some other book or some friends and so on. That is the only way to learn things properly. So, jijnasa, one must be having queries. Okay, unless the mind opens up, questions, it questions whatever you have read, you will not learn mathematics. For any kind of learning that is necessary. All right? Okay, so now I give you full time to ask questions. I will wait for 10 minutes more. If you have no questions, then we will close. Okay. So here is another question again from Akash. What is the need of sub-basis when we have already a basis? Go back to the definition of basis and sub-basis. Sub-basis is a more general concept. For instance, start with any collection of subsets of X which covers X. For example, you can put X also there. Then you can generate a topology out of that. As a basis, no. As a sub-base, yes. So that is the nice difference between sub-basis and basis. Namely, starting with a collection, you take all finite intersections of them. So that's a larger concept, larger family, right? Now you take all possible unions. That will be a topology. Okay. But now the topology, the original thing is not a basis. Given an open subset in this topology, you can't guarantee that there will be, given a point, there will be a subset, there will be a member of the original family which will be contained inside that. Only you have, after taking the finitely many intersections, one of those will be there. Okay, that will be basis. The original thing is called sub-basis. Because the inverse of sets under a function is well behaved under both, intersection as well as union. Verifying continuity, on open subsets, you have to show inverse of open subset is open, right? The first thing you observe that it is enough to show that on a basis it is enough. F inverse of some B is open for every B inside a basis, then it will be continuous. But the same thing is true for sub-basis also. So that reduces the workload for verifying a function whether it is continuous or not. So there are several instances wherein you will have to go to sub-base to do this job. Another important application of sub-base comes when you study product of compact spaces. So you have to wait for that. Okay. There is something attributed to Alexander, the proof of that arbitrary product of compact species is compact, Tikhonov's theorem. Okay, there are several proofs of Tikhonov's theorem. One of the proofs uses the concept of sub-basis very strongly. Okay, so that is something not, there is no continuous function or anything. All other applications are in the case of continuous function. Just look at real valued functions. Okay, suppose you show that all half open intervals, all the rays, the inverse image is open, and that's enough. For all x bigger than r, if inverse of that, all points such that fx is bigger than some r, all points of fx is bigger than some s. So for r and s different, if you show these are open subsets, f will be continuous. You can show that separately, that's easier quite often. Okay. So the subbase has several such roles to play. If you have any comments also you can make. By the way, please use the forum wherein you put the queries. Your tutor will also answer them, okay, especially for things which you have doubts in assignments and so on, or any other part of the questions you can ask. If there are several queries and tutor is not answering very efficiently, then we will have another session of live session like this, in which I will try to answer them. Okay. So feel free to ask questions and make comments. Thank you. So let us close now today.